Hello, physics students. So we're going to look at the lesson on measurement here. As shown in the image up here, measuring the length of things and really making lots of other measurements too. It's important to understand how to carry out the measurements and also the degree to which you're certain of the measurements. And this, gives us a picture of this bowl. You make sure that it's lined up with the 0 line, which it actually doesn't look like it's perfectly lined up to me based on the picture. And then you estimate where the end of it is at, and they may say 23.5, but it's possible somebody else could look at this and see 23.6, or maybe realize that the bolt's not exactly lined up with the 0 line and you need to move it back a little bit, and it might actually be 23.4 or 23.3. Alright, so we're going to learn how to make measurements with accuracy and precision, identify and quantify uncertainties, and we're going to use the metric or international system of units in scientific notation. Alright, so here's the assessment questions that we'll address later. And we'll talk about accuracy, precision, decimal places, and significant figures in this lesson. Alright, so let's talk about uncertainty. So all measurements have uncertainty, and that's because measurements are taken with some type of tool, some type of measuring tool. So you might see a measurement given, and it has this plus or minus and a number after it. And what that's saying is that we are certain of this number within 0.001 or 1 millimeter. So that means that you take this measurement, you report it, and you're saying that I'm certain that it's between 2.066 and 2.068, because that's what would happen if you added or subtracted 0.001 from this number. Now, in a lot of cases, the uncertainty is not written after measurements. Usually you don't do that when you write them down, say in class, and most of the time it's understood that whatever the last reported digit is the uncertain digit in the number, and usually the uncertainty is plus or minus 1 of whatever that last estimated digit is. Sometimes there are cases where it's maybe 2 or like 5, but usually plus or minus 1 of whatever the last place reported in the number is. And think about it, it wouldn't make sense to report any more digits than where there's uncertainty, because you would just be guessing if you tried to go out beyond the thousandths place in this particular number. Right, so why are measurements uncertain? Well, depending on how you're trying to measure something and what degree of precision you want, better ruler is going to give better measurements. So the ruler with more graduations is going to give more precise measurements than the one with less. Sure, you can measure the same thing with these, but the measurement that you get with this bottom ruler would give you better precision. All right. Okay, and there are times when more precision might not be merited, especially if you're just trying to get a general idea. Let's say you're estimating a project. You don't need to know exactly the length of the boards that will be used. You just need to know how much length of boards total you'll need to complete the project, and then maybe add a little bit to make sure you have enough. Or as they suggest here, wiggling child, you're probably not going to measure them as precisely, so the ruler with the larger spacings might be more useful there. All right, you can also have issues, environmental issues with trying to complete measurements. So when things get hot, they expand, so your ruler might actually change size a little bit as you're completing the measurement. If you're measuring liquids, the liquids expand when they're heated. So there's a variety of things that can go on there that maybe you haven't thought about. And then it's possible that you could have operator error as well. By the way, we don't want to be listing operator error as a source of error. So, generally speaking, if you find that you've made an operator error, in a rigorous scientific environment, you don't report that. You just redo the experiment. All right. So there are places where uncertainty doesn't matter that much, like the example they give is riding a seesaw. You really don't care how much the other person weighs. It's just, are they more or less than you? And then there are some places where it's very important to know uncertainty. For example, if you're trying to ship things to space, and while the space shuttle may not be running anymore, there are certainly space missions, satellite launches happening quite frequently, to the point where they're not really particularly newsworthy for the most part. All right, and then uncertainty is involved in what we call tolerances in engineering. It's pretty important that when you engineer something, that you are able to engineer it within a certain amount of uncertainty so that the parts fit as they're expected. Generally speaking, the tighter the tolerance, the more expensive the manufacturing process is. And if you've ever bought tools or just generally items, you might notice that a lot of times when you buy something that's significantly cheaper than another product that's supposed to do the same thing, you find that perhaps it's not been manufactured as well or to as exacting a standard or tolerance as you would like. All right, so accuracy is a term that describes how close a measurement corresponds to the actual or the true value of that quantity. All right, so a meter stick would not be particularly accurate if it was 1 yard long instead of 1 meter long. I think that's happened before. All right, precision is a description of how exact a measuring tool is, and that's also going to give you one way you can see precision with the measuring tool is repeatability. So if you use that measuring tool and take the same measurement 2 or 3 times, you should get the same measurement each time you take it. You may have noticed this in your own day-to-day life, where perhaps you've used a scale to weigh yourself, and I've had scales before where I would get on the scale, weigh myself one time, get off the scale, get on again, and I would weigh something different every time I got on the scale. And perhaps that's an indication that that scale's not particularly precise. And then also the graduation on the scale, we've sort of already talked about that, but you're going to get a more precise measurement with a scale or a measuring tool that has more or smaller graduations or less space between the markings. Now, when you report a measurement, the precision of that measurement is going to determine how many decimal places you report that answer to. Remember, I talked about how usually the uncertainty is plus or minus 1 of whatever the last place in the number is. So if you actually go out to more decimal places, you're indicating that there's more precision in the quantity that you're measuring. And the one that I'll draw particular attention to here is if you write down in a science class, you write down 2.10 and 2.100, those zeros out there are indicating that you actually measured that all the way out to the last zero there. I know in math, it really doesn't matter. 2.1, 2.10, 2.100. But in a science class where we're not working with pure numbers, we're working with measurements. So when you write those digits down like that, you're indicating that you did actually measure that place. So here's a diagram that pretends we're shooting arrows at a target, and you can have different situations. Like, for example, if you averaged all of these arrow shots together, well, they would average to the geometric center because they're evenly spaced out around. You take the average, that would end up being an accurate result because you hit the target, the desired center of the target, the desired answer. But your measurements were kind of all over the place, so you were not precise. However, if you hit the same place every time, that at least you were consistent, but you weren't accurate. This could happen if, say, you were using a balance in the lab, and maybe the balance hadn't been zeroed, and you were consistently a gram off of the correct mass. And then the last one here, all of the arrow shots hit the center of the target. So that means that you're not only getting the correct answer, but you're also precise because you're getting the same answer every time. All right, so significant figures are the digits that we use to write a measured value. And the significant figures is going to tell you the amount of certainty, and I guess also the uncertainty, in the measurement. So we've got a couple of answers here, or a couple of measurements here, and you can see this one has 4 significant figures, this one has 2. And we're saying that we actually measured this speed exactly to be 1.965. There'll be some uncertainty in the last digit, maybe plus or minus 0.001. This one's probably plus or minus 0.1. By the way, if you reported this 10 to the 5, so that would be like 240,000. So we don't know exactly, down to the individual mile per hour or meter per second, but we've got the first 2 digits of that number we know with certainty, and then the rest we're not completely sure. All right, so zeros in front of a number are not significant. They're just there as placeholders, and an example of that is if you say something is 5 meters, that'll be the same as saying it's 0.005 kilometers because there's 1,000 meters in a kilometer. So if we convert, that's what you get. All right, so both numbers have just a single significant digit. All right, changing units never changes the number of significant digits. So converting is not going to, or at least it shouldn't, make your original measurement any more or less uncertain. The only way that would happen is if the conversion factor you were using was significantly estimated. Like, if you're going from miles to feet and you said, I can't remember exactly, I think it's 5,000 feet in a mile, and it's really 5,280. So use a quality conversion factor, like don't round your conversion factors, and get as many significant digits in your conversion factors as possible so you don't lose anything, or you don't lose any precision as you're converting. All right, let's see. So count the number of significant figures. Do not include leading zeros to the left. Do include all other. Let's see. That's dangerous right there, because there's one condition where trailing zeros are not significant. So I imagine in this physics book they'll probably report with scientific notation a lot. But anyways, the rule I usually use is if there's a decimal point expressed, trailing zeros are significant. If there's not a decimal point expressed, trailing zeros are not significant. All right, so this one, leading zeros are not significant. There are 3 significant figures. And then this one, there are 5 because that's a trailing zero, and there's a decimal point expressed in the number. All right, so I'm going to stop here and come back with a part 2 to this video. Thanks for watching.